Hello everybody, this is Dr. Farhan Zamir from Biotechnica, Bangalore. For today, we'll be having an interesting discussion on how will AI change the face of bioinformatics in future. Let's try to dwell in. Welcome back. So for today, as we have discussed, we will look into the beautiful caption of understanding the role of bioinformatics and its combination with that of AI, and how is this particular marriage between the AI and bioinformatics can change the entire future of science. So let's look into the first component, that is, if I go into the basics, until now we were all applying the laws of our the human mind, and then with this we were trying to have a lot of hard work, and with the hard work the documentation and the creativity was being always put onto the paper. Now once this people as they got into adapting new technologies, then they thought that why do I do the experiments on the paper, can I translate onto the silicon chips? Now when they translated onto the silicon chips, at that point of time, new models such as in silico models actually came into picture. Now, this again went on for another 5 to 6 years, and later people thought, why don't I have something which is mimicking biology, and then I can apply it onto a technology. And then here comes a beautiful concept wherein we are trying to mimic a biosimilar, and this biosimilar is nothing but our brain. Now, people thought we will try to use the logic of how exactly our neural networks are being connected, and then the same logic of neural network was being put onto a circuitry, and this is how we wanted to analyze biology in a much better way. So now what we are trying to do is we are now utilizing the biosimilars, and onto the biosimilars we are looking onto the combination of biology with that of technology, so that we can make things easier, and second, we can make it rapid, reliable, and very importantly reproducible. So what are the various branches of AI? Now artificial intelligence has become a new trending norm. Now to understand the various branches of AI, let me start with a very important component, that is natural language processing, which is also called as NLP. Now natural language processing systems is mainly used for translation and very importantly classification and clustering and information extraction. Trust me, my dear friends, information extracting, when we are writing a review, collecting all the data on a particular topic becomes such an hectic work. And now using this NLP technology, what we can do is we can do a combination of keywords, and these combination of keywords will actually retrieve all the data from a given database, and this makes things much more easier. Writing a review, that is very importantly in terms of its meta-analysis, becomes extremely easy with NLP as a major language. Now, understanding neural network, very importantly, we are trying to mimic a particular in vitro or an in vivo model onto a circuitry, so that the complex multi-parametric studies could be put into one particular fashion, so that we can derive various kinds of patterns, and onto this particular patterns we are able to distinguish between various kinds of other parameters. Now how exactly neural networks works, we will also look into the future slides. Now another important branch of artificial intelligence is in speech learning. Very importantly, the translation of speech to text and text to speech creates a huge difference, especially with specially abled people. Okay, so this plays a very important role. Now coming on to the robotics, not to mention AI has a tremendous role in the application of robotics. Now as I was talking about the speech, now here comes something which is called as vision, wherein I am using AI into image recognition and machine vision. Then expert system. Now expert system is, imagine I have a patient and this patient has a particular ailment. Now as a clinician, somebody suggests the entire diagnosis, the detection has been done, but somehow the patient is not convinced. So normally what we do in our clinical practices, we always look for a second opinion. Now using artificial intelligence, this second opinion or a first opinion could be given by the machine production itself, and that is how AI plays a very important role in clinical diagnostics. Then coming on to cognitive computing. Cognitive computing is, it is not necessary that we need to remember everything. So here you have an assistant, and this assistant is an AI assistant, and such one of the beautiful, tool which has been actually developed is the chat GPT, which will act as a personal assistant to you. But now we need to understand how exactly I can use this AI open board for my understanding of bioinformatics, and how do I use it much effectively. This depends on the depth of knowledge what you have as a bioinformatician. Now, never to forget, it is machine learning, which is like deep learning, and predictive analysis plays a very, very crucial role in AI. Then finally, with all this, you create data. It is not a small data. Now you create a mammoth kind of a data, and this mammoth data is called as big data analysis. And this big data analysis becomes a very, very important, crucial component in your data revolution. Now, please remember, for any kind of machine training, I require data. I require a pilot data. I require a sample data, and this sample data comes from your big data. So the training of the machine takes place with this particular data, and once I have normalized the data, I have clustered the data, I have classified the data, then prediction becomes much more interesting and it becomes much more accurate. Let me try to also make you understand this about the prediction model in a minute. Now, AI technologies in bioinformatics, to be very, very precise, I can use AI technology in genome sequencing, genome expression analysis, protein classification, and protein structure modeling. Now, these are the 4 domains which are like absolutely booming off in applications of AI in genomics and proteomics. Now, these are the 6 major branches. So if I want to tell you in detail about the actual application of AI in bioinformatics, we start with the first component, which is called as genomics. Now, in genomics, you have the identification of the promoters and enhancers. You have the annotation of DNA sequence element. Then you can identify the exact splicing sites, and very importantly, investigation of nucleosomal organization becomes extremely easy with AI as one of the major tool. Now, coming on to the shifting gears onto the metabolomic part of it. So in metabolic part of it, I can look into the automation of data processing. Very importantly, when I look into an LCMS data or a MALDI data, here integration peaks and differentiation peaks becomes very, very crucial, and hence matching to that of a library, so that I can have an exact value of the peak, and this peak corresponds to a particular chemical or an analog during drug design, and the complete pipeline or the ligand identification or the lead optimization becomes very, very important. So hence you have the identification and quantification of the compound, and their structure becomes extremely easy. Then classifying samples based on their metabolic profile. Example, let me try to take up short chain fatty acids. Now, when I look into the short chain fatty acids, so there are good short chain fatty acids and bad short chain fatty acids. So looking into the various kinds of regulation and dysregulation of these fatty acids, I can consider them as a biomarker for good health. So especially in terms of gut microbiome or gut health, I can consider this as a major biomarker. So metabolomic component becomes much more easier with AI as its implications. Now, apart from that, I can move upon to proteomics, and in proteomics, protein, as you know, that they are like fickle molecules, but however, identifying sequence motif, prediction of protein function, then prediction of their secondary structure, and very importantly, the folding of the 3D structures could be exactly mimicked or could be better understood using AI technologies. Now, you have the epigenomics. In epigenomics, very importantly, defining cell type specific epigenomics becomes extremely easy. Then understanding the folding 3D genomes and their respective foldings becomes much more easier in terms of epigenomics. Now, coming on to the transcriptomics, wherein we will talk about the gene regulation component, and also since the gene regulatory components, the operons, they work at a different levels. Now, making them into one beautiful cluster and understanding their exact transcripts becomes much more easier, and you can also understand the alternative splicing patterns, which is one of the major crucial component in your transcriptomics. This could be easily understood. Now, amalgamating epigenomics and that of transcriptomics, you have something which is called as epitranscriptomics, and in epitranscriptomics, a greater emphasis is laid on the novel RNA modification motifs, and very importantly, you can predict various kinds of chemical modifications on a particular sequence, wherein you can have a reverse transcriptional signatures, and this is one of the major component of how exactly the applications of AI could be implicated into epitranscriptomics. Moving on forward, I can have the machine learning for a drug discovery platform. So as I had promised you that I would discuss upon how exactly a basic model of machine learning for drug discovery could have a greater implication. Let me try to take up an example of quantitative structure activity relationship studies. This is also called with an acronym of QSARS. That is, QSARS, that is Quantitative Structure Activity Relationship Studies. Now, let us try to consider an example. If you consider this particular cartoonic model, I have two molecules. So right now, remember, I have two different steps. The first step is to make the machine learn, and the second step is to extract. Once it has learned the entire algorithm, then I would put up another model and then try to see whether it is able to predict it in a better way or not. Okay, so I have part A and part B. Let us try to understand the part A component. Part A is I have two molecules. So these two chemical molecules are different, okay, in terms of their configuration and conformation of that particular functional group. So once I have these two molecules, we'll consider as molecule number 1 and molecule number 2 are the data sets what I am trying to teach the machine. And with this, as you know, directly 2D structures are not 2D chemical structures are not being learned by the computer. They don't understand, the computer does not understand the 2D structure. So hence what we need to do is we need to convert them into molecular descriptors. So this 1011001100111010 is the molecular descriptor which you are trying to convert it, okay, and what we call it as smiles. Okay, so these smiles are being created, and with this molecular descriptors, now what I do is I have an x-axis and a y-axis, or an x parameter and a y parameter. Now what is this x parameter? X parameters are the various kinds of chemical ligand molecules which have been set, and y is the bioactivity. I repeat, x is the various kinds of ligand molecules. I can have 10 ligand molecules, 100 ligand molecules, 1000 ligand molecules, 10,000 ligand molecules, depending on your voracity of the data. Okay, so if I just imagine that I have 10 molecules, and in this 10 molecules, all these 10 molecules will be my ligand, and hence they will be in x-axis. Now, what is in y? Y is the bioactivity what I have been expected out of that particular X ligand. And here what I tell the machine is, so Y is the bioactivity, and if you are qualifying, if the ligand is qualifying the bioactivity, then the parameter is 1. That means to say it is equal to active. And then if the parameter is 0, then it is inactive. That means to say the ligand molecule does not have that particular bioactivity. So now what you see is the entire data set, and this is called as data frames. So now, until now, whatever I explained, this is the part A of machine learning. Now, switching on to part B, once I have the entire data frame and my data is able to validate into 1 and 0, which is active and inactive form of the Y parameter onto the X ligand. Okay, so then what I do is I develop a model. So once I developed a machine learning model, so this will be the next tool which will help in predicting another molecule of my interest. Now, let us try to take up another molecule, which I call it as molecule number 3, which is entirely different from the data sets what I have actually used, but I am trying to see whether the machine is able to pick up the pattern. Now, with this as a molecule number 3, again, I need to convert it into the molecular descriptors. Once I have the molecular descriptors, I will feed molecule number 3 onto the model and let me see whether the molecule is able to predict well. Now, in the prediction, because again I said Y is your bioactivity, with Y I see 1. So if there is 1, this is an indication that the molecule 3 is actually active, because we now know that 1 is equal to active and 0 is equal to inactive. So since the molecule number 3 is predicted for Y parameter as 1, so I predict okay, or the machine is trying to tell me that this particular molecule is active for the Y bioactivity, what you are looking as a researcher. So this is a prediction. Now, please remember, whatever we are trying to look upon is one-to-one interaction. There is one ligand and a one target. So there is one-to-one interaction in an in silico system. But however, in 80% of the cases, this is true. But however, you have another 20% wherein you need to validate these particular hypotheses. And this has been only done with your wet lab studies. So once I know the prediction, okay, so what I can do is I can also go for further extraction of very important features, and this feature important, extraction could be done by the model itself, wherein again, if I have, there are various bioactivities. Among the various bioactivities of Y, which is the bioactivity is maximal and which is the bioactivity which is minimal or moderate, this kind of a graphical presentation could be created with your machine learning system, and that is how, the drug discovery pipeline with artificial intelligence works. Now, another example for you to understand in a much better way is, rather than a structure chemical protein interaction, let us try to take up a big data. I have an hospital. With this particular hospital, I have collected huge amount of data in terms of electronic medical records, in terms of hospital data, in terms of cloud sharing data. I have all these data coming into one particular pool, what I call it as big data. Now, this would be my input data. Now, once I have this input data, I would like to have the application of AI onto my big data. And when I do this, I use two different languages. One, I can go on to a machine learning approach, or I can use the NLP, that is natural language processing system, to process my data. And as an application out of it, okay, now I am, interested with a very important application, that is, reproductive medicine. Now my focus is on reproductive medicine. And when I look into it, again, the tool says, the algorithm or the machine says, you can still look into it in two different ways. One is the research and experimentation part, which has been taken place, and also in the clinical practice, which has been has been analyzed with that particular data. Now, what is the advantage of this? Now, the major advantage is you have the cost effectiveness. So the cost effective assessment for a given diagnostics could be done using this particular model. And very, very important, which will be a boon for all clinicians, is you can have clinical decision systems. So you can have your own prediction, and then your with your diagnosis, you can also check with that of your the data which comes from AI, and then you match the both. Now, this will act as an aid, this will act as an help, okay, additional help to the clinician, so that they can actually diagnose it in a much better way. Now, these kind of applications could be used for sperm selection classification, then oocyte classification, or embryo selection during artificial in vitro fertilization or artificial insemination. Okay, then you can also use this kind of a clinical data for robotic surgery. Because again, as we have discussed the various branches of AI, I can still use it for robotic surgery and very, very important outcome prediction. So, before I actually perform, I can actually predict what exactly can happen with this particular clinical patient. So this is how big data and AI and bioinformatics can actually change the entire future of the mankind. And with this, I just wanted to thank you people for your patience, and very, very importantly, I request you to get upgraded, because upgrading is the only key. Now, just learning bioinformatics is simply not sufficient. We need to adapt the technologies of molecular biology. We need to adapt the technologies of AI, ML, deep learning, and then bloom up with a new concepts. And these new concepts will open up a new arena for the entire world, which is the major necessity for this particular society at this particular point of time. So here at Biotecnika, we have various kinds of certification and internship programs. I request everybody to have a look on it and visiting our website of Biotecnika and Rasainika. Thank you very much for staying connected. All the very best.